Bismillahirrahmanirrahim. Today we will cover part 3 of our chapter 5, brakes. Today's chapter topic is anti-lock braking system. Previously we have covered two parts. In first part we have studied about the block diagram of the brake system in complete, how it works and different parts of front brake, the disc brake and the rear brake, the drum brake and their parts and advantages and disadvantages. In second part, we have talked about the hydraulic brake master cylinder and then different valves which are there in the brake master cylinder. Now, today is the third part of our chapter 5 brake, and topic for today is anti-lock braking system, which is different than the conventional braking system. So let's see what is the anti-lock braking system is, or ABS system in general. Anti-lock braking system, ABS, helps prevents the wheel from locking during sudden braking, especially on slippery surface. This helps the driver to maintain control. Now let me give you a general concept or idea. In normal vehicle, in which we do not have the ABS system, when you apply a brake, means depress the pedal, the brake mechanisms comes into action and the brakes stops the wheel. When brake stops the wheel, it get locked. When it gets locked, the contact area between the tire and the road is the same, but it gets locked, wheel is locked. So that area is continuously in contact with the surface and it tried to skid till the brake forces overcome the driving forces. Okay, this is in normal. So there is a skidding action in normal or conventional braking system. So the amount of stopping distance is increased because of the skid of the wheel on the surface. But if we are equipped, vehicle is equipped with ABS system or anti-lock braking system, the skid portion that is minimized. We apply a brake, the brake mechanism comes into action and it stops the wheel and there is pulsation. So wheel is not locked. So the contact area changes with that pulsation. So there is friction remains there. So the skid distance is shorter and the whole braking distance is shorter than the conventional braking system. So this is how the general concept or idea of the conventional or anti-lock braking system is. So anti-lock braking system helps prevents the wheel from locking during sudden braking, especially on slippery surface. This helps the driver to maintain control. Anti-lock brakes increases safety because they eliminates lockup. Lockup means when brake and wheels are lock up and minimize the danger of skidding. So the skid distance is minimized, allowing the vehicle to stop in a straight line. ABS also allows the driver to maintain steering control. So it also helps the driver to maintain the steering control during heavy braking so that the vehicle can be steered to avoid an obstacle or another vehicle. ABS can improve braking when road conditions are less than ideal. So if your road conditions are less than ideal, ABS can improve your braking, as when making a sudden panic stop or when braking on a wet or slick road. ABS does this by monitoring the relative speed of the wheels to one another. Because there are sensors installed on the wheels, they are monitoring the every wheel speed. So every wheel speed is monitored electronically and the hydraulic pressure is applied with relative to that force on that wheel. So it's Monitoring the relative speed of the wheels to one another, it uses this information to modulate brake pressure as needed to control slippage and maintains traction when the brakes are applied. Now let's see. The brake slows the rotation of the wheel, but it is the friction between the tire and the road that stops the vehicle and allows it to be steered. So brake basically stop the rotation of the wheel, but it is the friction between the tire and the road that stops the vehicle and allows it to be steered. If tire traction is reduced, means the contact at that contact point, stopping distance increase and the directional stability of the vehicle suffer. The traction is defined in terms of tire slip. So the traction is defined in terms of tire slip, which is the difference between the actual speed and the rate at which the tire treads move across the road. So traction is defined in terms of tire slip, which is the difference between the actual speed and the rate at which the tire treads move across the road. A free rolling wheels has nearly zero tire slip. A free rolling wheel has nearly zero tire slip, while a locked wheel has 100% tire slip. A free rolling wheel means the contact area is changing, so there is a zero tire slip. When it is a locked, it means this point is locked, so it has a 100% slip with the ground. When the brakes are applied, the rotational speed of the wheel drops. The tire slip increase because the treads move across the road slower than the actual vehicle speed. This slips creates friction that converts kinetic energy into braking and cornering force. Now let's see, a maximum braking traction occurs when tire slip is between 10% and 20%. So the maximum braking traction occurs when the tire slip is between 10% and 20%. A rotating tire has zero slip and lockup wheel has 100% slip. Now let's see, this vehicle is moving, tires not rotating. When tire is not rotating, we have a 100% slip. The vehicle is moving and tire is also rotating, so we will have zero slip here. Now tire slip and braking distance. Tire slip and braking system distance depends upon the surface on which you are moving in. On dry or wet pavement road, the maximum braking traction occurs when the tire slip is held between approximately 15% and 30%. Okay. On snow or ice-covered pavement, the optimum slip range is 20 to 50%. In each case, if tire slip increases beyond these levels, the amount of traction decreases. So slip range should be in these ranges. If it is increased from these ranges, the amount of traction decreases. A skidding tire with 100% slip provides 20 to 30% less braking traction on dry pavement, and this is generally turns on slippery road as well. True as on slippery road as well. In nearly all the cases, the shortest stopping distance are obtained when the brakes are applied with just enough force to keep the tire slip in the range where traction is greater. Now let's see this graph. On our x-axis, we have tire slip from 0 to 100%, and our y-axis, we have this cornering lateral force, means we are turning in, so the lateral force is applying there, and braking force which we are applying. So these dotted lines are your cornering lateral forces, and these blue lines are your braking forces. And this is the percentage of the tire slip which cover on these type of surface. We have dry concrete, dry asphalt, wet asphalt, snow, ice. So the braking force is applied, and this is the tire slip in this region. Depends upon the surface which we are moving. Note, all anti-braking system stops controlling the wheel brakes when the vehicle speed drops to about 5 miles per hour or 8 kilometers per hour. The wheel speed sensors are often not accurate that these low speeds and loss of vehicle control at this low speed is unlikely. So this is the limitation of your ABS system. At slow speed means 5 miles per hour or less than this, the wheel sensors do not give the accurate information. So when there is no accurate information, the ABS systems do not perform fully 100% efficient. So there is likely chances that the vehicle will lose control or lose at low speed. There are two limitations, no ABS limitations. There are two situations in which an anti-lock braking system will not provide shortest stopping distance. So what are those two limitations? The first involves straight stop made on a smooth drive pavement by an expert driver. Under these conditions, a skilled driver can hold tire consistently closer to the ideal slip rate than the ABS can. We will see this graph. I repeat again, the first involves straight stop made on a smooth dry pavement by an expert driver. Under these conditions, a skilled driver can hold the tire consistently closer to the ideal slip rate than the ABS can. This is possible because current anti-lock braking system may allow the amount of tire slip to drop as low as 5%, which is somewhat below the point where maximum tire traction is achieved. However, for the average driver or under less than ideal condition, anti-lock brakes will almost always stop the vehicle in a shorter distance. So let's see this graph here. On our x-axis, we have the tire slip from 0 to 100%. On 0, we have a free rolling wheel, and here 100% means locked wheel. The tire slip is maximum at the locked wheel. On our y-axis, we have braking and corner forces. Blue one is the braking force and red dotted is the cornering forces. This is the region when your expert driver slip range, it can take shorter distance than your anti-lock braking system when we have a drop as low as 5% of the tire slip. So braking effort is increasing, cornering effort is decreasing. Then after certain point, the braking effort is minimizing, but the expert driver will control the vehicle in a shortest possible range as compared to the anti-lock slip range. This is the one of the limitation. Second is the other situation in which anti-lock brake system will not provide the shortest stop is when braking on a loose gravel or dirt or in deep fluffy snow. So when the ground condition or the moving road condition is we are having a loose gravel or dirt or deep fluffy snow, the shortest possible distance in braking cannot be achieved by the ABS system. Under these conditions, a locked wheel will stop the vehicle faster because loose debris buildups and forms a wedge in front of the tire that helps stops the vehicle. So the loose debris, front wheel and the rear wheel form a wedge here. Then it will help to stop the vehicle. Anti-lock braking system will prevent this wedge from forming. So when we have an anti-lock braking system, this wedge will not be formed there. So some vehicle with anti-lock brakes have a switch on the instrument panel that allows the systems to be deactivated when driving on these kind of road surface. So to avoid this type of limitation, in some vehicle we are equipped with a switch on the instrument panel. If we switch on that, the anti-lock braking system is deactivated and we can have this Conventional braking system in which the wedge is formed on loose gravel, dirt, or deep fluffy snow. A wedge of gravel or snow in front of a locked wheel can help stop a vehicle faster than would occur if the wheel brakes were pulsed on and off by anti-lock braking system. Another situation where the anti-lock brakes cannot defy the laws of physics occurs when the vehicle enters a corner traveling faster than it is physically possible to negotiate the turn. So when we are turning or we are cornering, then the situation is that the anti-lock brake system cannot defy the laws of physics. In this situation, anti-lock brakes will not prevent the vehicle from leaving the road. However, they will allow the vehicles to be slowed and steered in the process, thus lessening the severity of the eventual impact. Being able to steer and control the vehicle during rapid braking is one major advantage of anti-lock braking system. Now the components and the operation of the ABS system. ABS components are basic components that are common to all anti-lock braking system includes the following: wheel speed sensors, electronic control units, ABS warning lamps, hydraulic modulator assemblies with electrically operated solenoid valves. So these are the four major or common components used in a ABS system. Let's see one by one. Wheel speed sensor. All ABS systems control tire slip by monitoring the relative deceleration rates of the wheel during braking. So wheel speed is monitored by one or more wheel speed sensors. So all the wheel are equipped with wheel speed sensors. If one wheel starts to slow at faster rate than the other or at faster rate than that which is programmed in the anti-lock control module, it indicates that the wheel is starting to slip and is in danger of losing traction and locking. So with the help of the speed sensor, we are monitoring the locking of a wheel or slipping of the wheel. The ABS responds by momentarily reducing hydraulic pressure. So when it is slipping or losing traction, so ABS will respond to that and the hydraulic pressure going to that wheel will be reduced to brake the to the brake on the affected wheels or wheels. This allows the wheel to speed up momentarily so it can regain traction. So when the hydraulic pressure is reduced or minimized in that wheel, this will allow the wheel to speed up momentarily so it can regain traction. As traction is regained, brake pressure is reapplied to again slow the vehicle. So when the vehicle will be moving, the traction will be gained. So again, the pressure will be applied more to stop that wheel. This cycle is repeated over and over until the vehicle stops or until the driver eases pressure on the brake pedal. So this is how the wheel speed sensor works, and it gives the it gives the actual information to the control unit, and then control unit gives the signals to the hydraulic system, and hydraulic system maintains the pressure up or down to stop and gives the pulsation to that wheel. Then the control valves. Electrically operated solenoid valves or motor-driven valves in case of Delphi ABS6 applications are used to hold, release, and reapply hydraulic pressure to the brakes. So wheel speed sensor is giving the information. That information is going to the electric unit. Then electric unit are controlling the solenoid valves in the hydraulic system. That solenoid valves or control valves used to hold, release, and reapply hydraulic pressure to the brakes. This produces a pulsating effect. So hold, release, and reapply and many a time in a minute in a braking system, and the pulsation effect is witnessed, which can be felt in the brake pedal during hard braking. The rapid modulation of brake pressure in a given brake circuit reduces the braking load and on the affected wheels and allows it to regain traction to prevent lockup. The effect is much the same as pumping the brakes. Effect that except that the ABS system does it automatically for each brake circuit. Actually, we are only pressing the brake pedal and this is happening continuously. The pulsation effect is happening continuously and in the lead circuit and at speed that would be humanly impossible up to 20 times per second depending upon the system, some cycles faster than other. So the pulsation effect is 20 times per second or more in a circuit so that the brake is effective. Now, a typical stop on a slippery road surface without anti-lock brakes, notice that the wheel stopped rotating and skid until the vehicle finally stops. Now, on x-axis we have time, on y-axis we have a speed. Blue shows the vehicle speed, green one is the wheel speed. Now we are applying the brakes or hydraulic pressure here. We are applying brakes here. Speed is this much. Here, wheel stops rotating. Braking effect comes into action. Wheel stops rotating. Now, and from this point till this point, your here your wheel stops, but the vehicle is still moving, and vehicle stops here. So this is the wheels lock and skidding distance, which covers due to the inertia or the speed which we are covering. System configurations. There are three types of system configurations. 4-channel ABS system. On some applications, each wheel is equipped with its own speed sensor. So if we have a four-wheel vehicle, so each wheel is equipped with its own speed sensor. This type of arrangement is called four-wheel or four-channel system since each wheel speed sensors provide input for a separate hydraulic control circuit or channel for that wheel. The term channel always refers to the number of separate or individually controlled ABS hydraulic circuits in an ABS system, not the number of wheel speed sensor electrical circuit. So this is the 4-channel ABS system, now 3-channel ABS system. Some four-wheel ABS system have a separate wheel speed sensors for each front wheel, means the right and the left front wheel have their separate wheel speed sensor, but use a common speed sensor for both rear wheels. So the rear both wheel have a common speed sensor, and that rear wheel speed sensor is mounted either in differential or the transmission. So the both rear wheel have a single or the same speed sensor that is mounted in either the differential or the transmission, but the front both wheel have their separate speed sensor. That is the 3-channel ABS system. Single channel ABS system. The front wheel have no speed sensor and the only single speed sensor mounted in the differential or transmission is used for both rear wheels. So there is only one speed sensor and that is mounted in the differential or transmission, which is used for the both rear wheel. Rear wheel anti-lock brake system are typically used on application where vehicle loading can affect rear wheel traction, which is why it is used on pickups, trucks, and those which carry weight at the rear. Now, integral and non-integral and other system configuration. This is the 4th configuration. First 3 was due to channels, and this one is the integral and non-integral due to the combination of the assemblies. Another distinction between ABS system is whether they are integral or non-integral ABS. Integral system combines the brake master cylinder and the ABS hydraulic modulator, electric pump and accumulator into one assembly. So all these brake master cylinder, ABS hydraulic modulator, electric pump and accumulator are in one assembly. Then we call this system as integral system. Integral system do not have a vacuum power booster. So when we are having all these assemblies in one assembly, sub-assemblies into one major assemblies, but we do not have this vacuum power booster for power assist and rely instead on pressure generated by the electric pump for this purpose. Non-integral is that in which we have the separate assemblies, not in one assembly. So now see the 4-channel ABS system. We have a left front, left rear, right rear. Every wheel has its own speed sensor. So this is 4-channel ABS system category. And 3-channel ABS in which left front and right front having this own speed sensor, and there for the rear left and the right left we have a common speed sensor. Either it is mounted on a differential or a transmission. So this is the 3-channel ABS. Now in single channel or 1-channel ABS, we do not have anything for the front and the right, front left or the right. We have only one speed sensor that is mounted in the differential or the transmission for both the rear wheels. So this is how the configuration is. So anti-lock braking system, a typical non-integral types in which we have this brake pedal. From the brake pedal, we have a vacuum power booster. And vacuum power booster, we have this master cylinder. Master cylinder, then it goes to the speed. We have a speed sensor here. Speed sensor, then this is the disc brake front, and signal is going to the electronic control unit. And we have this hydraulic modulator assembly here. Signal is coming from the speed sensor to the electronic unit, and from electronic unit, the signal is going to the hydraulic modulator assembly. That hydraulic modulator assembly is giving the pulsation effect at the brakes. Now, when we having an anti-lock braking system, which typical schematic drawing of a typical anti-lock braking system, we have this foot pedal, then we have a dual master cylinder, we have a hydraulic modulating device, then we have electronic control unit, and every wheel has its own speed sensor. They are giving information to the electronic control unit. From that electronic unit, control unit, the signal is going to the hydraulic modulating devices where we have control solenoid valves. From there, the hydraulic pressure is applying to the each wheel separately, whether it is a front or rear, and this means with the accurate amount of information which is we are receiving from the wheel speed sensor. So with this, we comes to the end of our part 3 that we have covered today, the anti-lock braking system. In next part, we will cover the dynamics of this braking system. So thank you very much.